Hi, I'm Rafael Sachs. I'm a professor at the Technion Israel Institute of Technology, and I'd like to introduce for you a deliverable 6.7 of the BIM to Twin project. BIM to Twin is a Horizon Europe 2020 project that deals with digital building twins for construction. The deliverable that we're talking about is deliverable 7.6. It's part of Work Package 7 on production planning. And in it, you will see how we do the first internal testing and validation of a software designed for prediction, evaluation, and analysis of alternative plans in the framework of a digital building twin. We will also see how we integrate the software with the database, graph database of the digital building twin. The purpose of our work in WP7 is to develop procedures and a software prototype for optimization of construction planning subject to lean principles, with particular focus on the plan, do, check, act cycle of production planning and control. And we will focus here on the check and act steps, where we use the information that we have collected to predict into the future, advise on the best way forward at any production planning cycle, and then deliver that information to production planners. So the software will predict possible outcomes of alternative production plans, and it will do that using simulation with an agent-based simulator, using the situational awareness provided by the digital building twin of the project. And it will read that from the database at any point in time before the next planning window, which may be a few days, a week, 2 weeks, or a month or more. The main aim is to make production planning proactive so that construction planners don't make decisions purely on the basis of their intuition or rough back-of-the-envelope calculations, but rather on the basis of very precise and bias-free status information. And they are aided by information coming from simulation, which plays out different alternatives into the future based on the understood behaviors of construction crews and projects. I'm going to start the introduction by trying to put this in the context of our overall BIM to Twin system. In the overall concept, we begin by designing and planning the product and the process, which drives the construction itself, building, of course, on the construction site results. And we're then monitoring that construction site in various ways, both on-site and off-site, and through the information systems of the companies. We're gathering raw monitored data. That requires a great deal of intelligent interpretation over here to convert that or to derive from that project status information, which describes the as-built product and the as-performed process. We can confirm, we can compare that status information to the intent information that we started from to evaluate conformance. And on the basis of that, we can derive knowledge about where we are in the project and what possibilities we might have for making changes. But before we go ahead and make those changes, we'd like to use our digital twin to predict what the outcomes of those changes may be. So here we come to the heart of Work Package 7, predict performance, simulation and analysis results, which are then provided to planners to go into the next cycle of plan, do, check, act. And what's only additional thing to highlight here is that we're going to use historical digital building twins to derive longer-term information, such as probability distributions for production rates and behaviors of crews, and so on. If we look at the workflow for the simulation, analysis, and prediction, then we can see that it works in the following way. We begin from the digital twin information, which gives us status about the project's current status. We ask the users for input about what their freedom of action is in terms of changing resource and material allocations, changing equipment, which may be tower cranes, pumps, formwork, etc. But it may also be their freedom of action in terms of the way they employ production crews, how their policies are for supply chains, and many other things. we have the status information and the user input. We can then automatically compile simulation scenarios, each of which represent an alternative plan that could be run in the next period. We can then simulate them, creating probability distributions of outcomes for each and every alternate plan. We can then compare them, and we can compare them on the basis of utility function that includes construction cost, duration, production rates, safety, sustainability considerations, but also, and most importantly, the production flow quality in the short term of the next production planning window. And that would include measures like the amount of work in progress, the amount of waste in terms of weighting of people or of materials, the number of locations that are actually being worked in, the cycle time for locations, and so on, all of which give a very good picture of the quality of production flow. We could then, this is not included in the scope of the deliverable you are seeing right now, but we could then also run automated optimizations of those using a genetic algorithm or similar tools. But either way, whether we apply optimization or we don't, we can take all the alternative plans that we evaluated and we can present them to users on a recommendation dashboard, and we will show you how that works, from which they can then make their selections, apply them as a new baseline plan, and then repeat the plan to check that cycle for the next production planning period.
Yeah. Hello everyone, my name is Jhonattan Martinez. Currently I am a postdoc at Technion, Israel Institute of Technology. I'm going to talk about the AP generation. The AP generation model aims to present user with the current project status and receive user input on the degree of freedom for plan modification from the baseline plan. More specifically, the model allows user to generate, enumerate, and export new AP by modifying or introducing new target, constraint, and simulation parameters. A first prototype was built using Excel and Visual Basic. The AP generation model contains a dashboard in which user can navigate across different submodels and create AP and their corresponding CSV file. As you can see, we have different buttons to generate and to export the AP. And also the user can navigate across the work breakdown structure of the project, the materials, the equipment type, and the crew type. After all the AP are created and the CSV file is generated, the simulation software is going to read the file. If we go to the work breakdown structure, this submodel enables user to visualize the project work breakdown structure and modify the prerequisite for each task. As we can see here, the user can modify the prerequisite for each task in order to increase the productivity and enhance the flow. In terms of the material submodel, the user can navigate across the whole material to modify the material condition and properties. For example, the batch size, the quantity, the arrival strategy, push and pull, the delivery frequency, and the delivery destination. In the case of the equipment, the user can modify certain properties, for example, the quantity, the maintenance rate, and the availability of each equipment. If we go back to the crew type, the user can change the number of crew, the production rate that could be probabilistic or deterministic. They can also modify the crew size, the production policy for each crew, the working hours per day, if they work overtime, the equipment assignment, and the equipment assigned hours per day. After the user compile all the APs generated, they need to go push the button of generate AP, and automatically the system is going to produce a new file that can be exported to the simulation software, only pushing the button of CSV file export. And after that, it's going to be saved in a specific location where the simulation software is going to take the information and begin with the simulation process.
We now come to the simulation module. Once the user selects the alternative plans that they want to explore, the Generate AP module will send these plans to the simulation module. Using the AnyLogic simulation engine, this module parametrically configures the construction site based on a given plan and simulates the remainder of the project duration. We then send the results to the Evaluate and Optimize AP module for further analysis. Now, for the simulation, we chose to model this construction site through the agent-based approach. Modern construction sites are complex socio-technical systems where technical processes and human decision-making intertwine. In a construction site are many different actors with their own agenda and priorities, and their behaviors changes when they face different contexts. This means to accurately capture this complex system and to predict its performance, we have to consider both the technical components and also the human factor that is involved in construction systems. For this reason, we chose to use the agent-based modeling approach. The agent-based method models the system as a collection of autonomous agents interacting with other agents and the environment. Interaction between agents give rise to emergent behaviors that is observable in the global scale. An agent-based model has two main components, the agent and their behaviors, which describes the way that they interact with themselves, others, and the environment. Furthermore, for autonomous or active agents like people, their interactions can be broken down into actions, what they do, and motivations, why they do something. Here, you see the user interface of the Enni logic software where we modeled a simulation. One of the key features of this software is a visual modeling interface that allows us to program and validate the simulation in a visual way instead of just lines of codes. On the left-hand side, you can see the main agents in the model, such as crew, supervisor, material, and supplier. Then in the main section, you can see the behavior of the trade crew agent class. Every agent class has its own set of parameters. They have perception variables to help them see and memorize the environment. They also have behavior functions, and on the right-hand side, the main behavior tree. The behavior tree specifies what actions and decisions the agent would make in a certain situation, and this tree would call on the relevant behavior functions that performs the actions and decisions. Here's an illustration of what goes on within a simulation run. Important to note here is that what we show is a single simulation run, but in our system, we will simulate every alternative plan hundreds and thousands of times to get statistically significant results. Finally, the module would transmit all these simulation data to the Evaluate and Optimize module, which my colleague will go over next.
The evaluation module collects and transforms the raw data from the simulation process into KPIs. Raw data such as event load, agent state load, and cumulative data are used for this purpose. This model and its functionality were incorporated into the Enni logic software. A set of KPI were created to evaluate the alternative plan, considering aspects such as cost, safety, environmental impact, quality, and flow. Each KPI contains subcategories that allow users to explore how the KPI results were obtained. For instance, the AP total cost for subcontractor is derived from the work packet cost and activity. After computing the KPI result for each AP, the model exports the result to the recommendation dashboard model. As you can see in the slide, we have the overall parameter used to evaluate the alternative plan, and also we are going to have the possibility to visualize the high level, the medium level, and the low level of each KPI used to evaluate the alternative plan. For instance, if we want to explore about the alternative plan cost, we can also visualize in the high level the total cost for the general contractor and the total cost for the subcontractor. In the case of the flow, for example, we have the total number of reentrant flow in the high level, and we have the total no value added time percentage. If the user wants to further elaborate in each indicator, they can also go to the medium level and the low level and visualize the result of the KPI. For example, in the flow, they can visualize the re-entry flow per location, and in the low level, they can go and see the re-entry flow per crew. Similar for the cost, they can visualize the earned value for work packet for the contractor, general contractor, and for the subcontractor. And also for the quality, they can go and check the total number of defects that are associated to the total number of defects for the alternative plan. And also they can go to the low level and visualize the total number of defects per activity. The optimization model. The KPI user for the evaluation model was transformed into an utility function. This function allows user to prioritize one or more factors during the AP optimization process. Optimization is the process of finding the optimal combination of conditions resulting in the best possible solution. The optimization process will be performed using the following utility function, which consider aspects of the cost, safety, quality, environmental impact, as well as flow. As you can see in this formula, the user can establish different weights based on their degree of freedom and the scope of action. For example, if they want to maximize the cost in the utility function, they can put more weight to the cost. Then they need to reduce the weight in the other factors. If they want to balance the function based on the cost and duration, they need to distribute the weight between the cost and duration and put different numbers that balance the weight. If they want to balance all the factors and obtain the optimal solution that give the best cost, duration, flow, safety, and environmental impact, they need to put the same weight for each factor.
Welcome to watch BIM2Twin Work Package 7 Recommendation Dashboard Prototype Demo. This is the Recommendation Dashboard landing page. Purpose of this view is to show the site manager that what is the situation at the site today and where they should focus their attention. By clicking the matrix cells, the user may view the status of their subcontracts. Here we can see that the work package 4 is missing materials. Finally, on the right side, there's the summary of forecasted outcome for the baseline plan and a summary of alternative plans from which the user may click to view them all. Here is the overall view for comparing alternative plans. The purpose of this view is to show all alternative plans generated by the simulation engine. Therefore, it is essential that here the user may easily sort the numerous alternative plans according to their objectives. This is enabled by selection of first, second, and third priority areas. According to this user selection, the plan total score is recalculated. This way, the user may easily sort the best alternative plan for them. Additionally, this view visualizes the top-level KPIs and completion date, overall cost, and quality score. Finally, the user may select few alternative plans to review their content in more detail in the parameter comparison view. Here, the main idea is to distinctly highlight the parameters that have been altered. Additionally, the fixed parameters are also shown, but visually faded as they have not been changed. Here also, the goal is to enable users to compare different plans according to their KPIs, and also on click to show further information about what actually has been changed within each different alternative plan. Final step is to select one of these alternate plans for final comparison. This final comparison is envisioned to be made for at least schedule, cash flow, and resourcing. For this recommendation dashboard prototype, we drafted the first version of the schedule comparison view. Here, the user may easily compare two different schedules in the flow line and Gantt chart views to see how they compare to each other. All in all, this view is meant for easy to understand the comparison between best alternative plan and the baseline plan. Therefore, The end of recommendation dashboard workflow will be either to share this information with others or to implement the selected alternate plan as the baseline plan for the production. Thank you for watching BIM Twin Work Package 7 Recommendation Dashboard Prototype demo.
In this section, we would like to demonstrate our integration with the digital twin platform developed in Work Package 2. Our simulation system needs to retrieve project status and information from the digital twin database to facilitate an alternative plan generation and process simulation, as our colleagues have discussed in previous sections. The BIM2Twin digital twin is hosted in this cloud platform called Technion, which is a graph-based research platform developed by our partner, Orange. Now I'm going to show you a bit how this platform works by querying some data from a project. First, let's sign in. And now let's make the query. Here we can see a 3D view of the Surila pilot project graph database, and it contains all the project information such as activities and work packages, but it also contains building elements such as doors and windows. Now let's take a closer look to one of the apartments of this project. Here in the center we can see a work package called Indoor Works Apartment 1, which has different activities such as plastering ceiling or painting ceiling. Each one of these activities has their own resource assignment, including work crews, materials, and equipments. The Technion platform has an application programming interface, or API for short, that allows our systems to connect and retrieve or send information. To test this API and show you how it works, we are going to use this software called Postman. Before retrieving or sending any data, we will first need to authenticate using this authentication endpoint. We will need to send our credentials. We will receive a token as a response. Then we will need this token, and in any of the other queries, we'll need to add a header, the authorization header, with the value of better, space, and the token we just received. We will also need to add this accept header with the value application JSON, which will tell the API that we are sending and retrieving information in the form of JSON objects. Finally, we will need to add the body of the request, which we can copy from the Technion platform, and we just need to modify the domain that we are going to query. In this case, we are querying the apartment 1 of the Surila pilot project. Now let's send the request, and we will receive the response in the form of a JSON object. Finally, we use algorithms to interpret these raw object data and transform them into these Excel tables for our system to use.
In order to demonstrate the full system pipeline, we will present a use case using data from the pilot project called Surela. This project is a 4 residential building with 8 floors each. Each building contains 46 apartments in total, with 50 meters square average area for each. The location of the project is Espoo, Finland, and the project estimated duration is 1 year and 9 months. The problem detected is that the supply chain disruption occurred during the second month of the project. The site manager wants to accelerate the project. Because of that, he tried to detect the possible bottleneck, and for this specific case, he detected that the plastering activity has a high work quantity in the next month with low production rate compared to other activities. To address this problem, he proposed 3 alternatives. The first alternative is increase the plastering crew size between 0 to 100%. The second option is replace the plastering crew with a more skilled crew. It means increase the production rate. And finally, he proposed change the control policy to reduce the work in progress. For example, prioritize the finishing the whole apartment and the whole floor. In order to address this problem, we need to now evaluate the different alternatives that the design engineer proposed. To do that, we need to create different alternative plan. The first alternative plan need to incorporate the possible alternative, that is increase the plastering crew size between 0 to 100%. It means that we need to go to the crew type, then check for the plastering crew, and then we need to modify the size. In this case, the current size is 1, we need to go and put 2. After that, we need to go and generate the AP. The second alternative implicates that we need to replace the plastering crew with a more skilled crew. To do that, we need to go again to the crew type and then modify the crew size and put in the previous one, and then we should modify the plastering crew production rate. Based on FIRA statistic that was provided previously, a more skilled crew has a production rate of 12. We put 12, we come back to the main dashboard, and then we generate a new AP. The final alternative is change the control policy to reduce the work in progress. Example, prioritize the finishing the whole apartment and the whole floor. To do that, we need to go to the crew type, then we need to check for the plastering crew and change the production policy associated with this crew. As we can see here, we have 4 options. For this specific case, we are going to select the number 2, that is oriented to fulfill this object. We need to come back to the main dashboard and generate the alternative plan by pushing this button. After we generate all the alternative plan, the user needs to go and then push this button to generate the CSV file. Then this CSV file will be stored in a location in which the simulation software is going to reach to proceed with the simulation process. These 3 alternative plans plus the baseline plan are simulated in our engine hundreds of times to get the statistical significant results. These results are then evaluated and presented to the user in the recommendation dashboard. The user can see here that the alternative plan to change the control policy result in the best KPI score. We would like to end this deliverable with a summary and a few words. In this deliverable, we present the system architecture of the Work Package 7 planning and control software. We then explain the functionalities of each module and show a snapshot of the prototype. We also test the integration with the digital building tool platform developed by Work Package 2 through API calls. Lastly, we demonstrate the software pipeline with a small use case. For the future, we will further develop the software according to the requirement layout in deliverable 7.1, 7.2, and 7.3. We also plan to automate the software pipeline and validate the system through the pilot project within the BIM 2 Twin project.